The idea of sequences is some set of numbers that has some kind of pattern, some kind of order in it. So an example of a sequence would be 1, 2, 3, 4, 5, dot, dot, dot. Okay? So what's that? Yeah. Okay, so this is a sequence. Now there's a whole bunch of different kinds of sequences that are out there. This happens to be 1. We can do 1, 3, 5, 7, dot, dot, dot. Usually you need at least 3 numbers to be able to tell what a sequence would be. Sometimes you might need even more, maybe 4 or 5. But just because I give you 1 or 2 doesn't necessarily mean you can do a pattern here. This one could be, for this one the pattern could be 1, 2, 4, or it could be 1, 2, 3. Right? It could be a multiplying by 2 every time. We don't really know. Okay, this one could be a add 2 every time, or it could be a multiply by 3 every time, or it could be a power reduction every time. It could be any different one. So you need at least 3 is like the minimum. 4, maybe 5 are kind of the good things to find. Okay. For today, what we're going to do to start with is just figure out how we find any kind of sequence. Now, the general notation for this, if I want to find a term in a sequence, the general notation is going to be a sub n. Okay. So a sub n is going to be a term in the sequence. Okay. So if I want to find any term in that sequence of a sub n, it might have some formula with n's in it. So for example, it might be like a 2n minus 1. Okay, so they're saying that the a sub n term, this is just whenever they use a, usually it stands for one individual term in the sequence. Okay, so one individual term at the nth term is going to be using this formula to give me one term in the sequence. So if I want to find a sub 1, let's say, okay, that's the first term in the sequence. Okay, that's what the A1 stands for. 1 is the first term, and then A is the term that it is. Some sequences start with A sub 0, and that's fine. It's kind of up to you, arbitrary. There's no good reason for it. Just some of them start there. So if I want to find A sub 1, I would just plug a 1 in for the n. And so 2 times 1 minus 1 would be 1. So A sub 1 would equal 1 on this first one. Okay?
Have you ever had a negative n?
You could, yes.
Like would they
Usually,
start like negative 2?
I mean, technically you can start at whatever you want to start at. Usually it's 0 or 1, like the very, very common ones, but usually not the negatives. Okay? So some of your problems now are going to be very simple, and it's going to say find the first 5 terms of this sequence right here. Okay? So the first 5 terms of the sequence, we just find the first term, a sub 1, find the second term, a sub 2. Can you just what? That's adding them all together. That's a little bit. Okay, so we're not actually adding together. We're just finding out the terms in the sequence. Questions?
Did you say it was whole numbers already? Like each sequence, like
whole numbers?
N, yeah.
N is counting. So those are going to be on the number. Yeah. Usually you would go 1, 2, 3. That's just the counting mechanism. Right. Exactly. Okay. A sub 2, we're just going to plug a 2 in. So we're going to get 4 minus 1. So 4 minus 1 is 3. A sub 3, the third term. So plug in the third term there. Plug in a 3, I get 6 minus 1, so 5. Now, once you kind of get there, you might start to recognize the pattern and be able to kind of run from there. A sub 4, plug in 4, would be 8 minus 1, so 7. And then, sure enough, I think we got it. So A sub 5 would equal 9. Okay? So now this sequence right here that I wrote has a specific name. They're probably not going to ask you for this name, but it's good to recognize. I don't know if you guys remember this, but there was 2 major sequences that we dealt with. First one was called an arithmetic sequence, and this one's an arithmetic sequence because it has what they call a common difference. Okay, so you go from here to here, here to here, here to here. You're doing the same thing every time, right? Now, how much are we adding every time? Adding 2, right? So the common difference here would be a 2 in what they call an arithmetic sequence. Okay, if you're adding the same number every time, that part of it is arithmetic. Okay, so usually the way to do it, the difference between these 2 is 2. Right? You guys notice that? And then in my formula here, notice there's a 2 right here. Okay, so that 2 is kind of like when you do your arithmetic. That 2 is what you're going to put in it. Now we have super fancy formulas from the past.
Subsequence.
Yeah. Well, no, not subsequence. We're not getting into there. I'm talking about a sub n formulas. Okay, and I think we had a sub 1, plus, and then it was d parentheses n minus 1. There were some pretty exact ones. We can kind of guess and check a little bit now versus using exact formulas, okay? But we do know the common difference here is 2, and so that's why it would be a 2n. And then we just have to tack on whatever number gets us to our first term if we plug in a 1. So you can do a little bit of guess and check there, or you can kind of remember those fancy formulas if you want to. Okay? All right. So if you start at 2, so you can start the sequence at 2, sure. So if you're saying if it was 2, 4, 6, 8, like that, sure. It's still a difference of 2, so this would be a 2n, right? And then if I plugged in a 1 right there, I don't have to do anything with that. So 2n would be the formula for this one. If I plug in a 1, it's 2. If I plug in a 2, it's 4. 3, 6, and so on and so forth. Okay? So the 2n part is kind of the common theme there because it's what they call arithmetic. Okay, you're adding the same thing every time. Okay, now let's go ahead and do this one. Let's go ahead and say we have b sub n. And we'll say b sub n is 3 to the n minus 1. And we want to find the first 5 terms of this sequence. Now you can mess around in your calculator a little bit and figure out some certain values for how to do this. Nothing stopping you from typing this like into your y1. There's even a sequence mode on your calculator if you want to mess with that a little bit. You can type in values, whatever you want. You can do tables, right? Table would be a great thing on this one, right? Your x and y tables. So however you want to cheat there, I'm okay with, because this stuff is really not that mathematically that hard. You just plug it in numbers, right? So I think we're going to be okay there. But if I do b sub 1, it means just plug in a 1. And so if I plug in a 1, I get, let's see, 3 minus 1, so I get 2. B sub 2, plug in a 2, so I'm going to get 9 minus 1, so that's 8. B sub 3, plug in a 3, it's 27 minus 1, so 26. B sub 4, plug in a 4, 3 to the 4th is 81 minus 1, so that's 80. Oops, that's going to be an 80. And last one, B sub 5, 3 to the 5th, 242, 243, and then minus 1, so 242, 242. Okay? And like I said, you guys can cheat a little bit, put those on your calculator. Feel free to utilize that. There's nothing wrong with that. Okay, so there's our sequence. Now, today what we're going to try to focus on is trying to figure out how to get these sequences, like they give you a sequence of numbers, and trying to write the nth term, trying to write the a sub n formula that'll give you each individual term. That's where this stuff, I think, becomes a little more challenging, and you need more patterns to be looking at here. Okay, as it's on this one, it's not real obvious like what we're adding by or multiplying by. So these ones get a little bit tricky. For example, if I went from 2 to 8, let's say I add 6. If I go from 8 to 26, how much do I add? Is that 18? Right? So not really a good pattern going on there, right? So sometimes you might want to look at a sequence of numbers and maybe add 1 or subtract 1, and it might be able to pop onto a sequence that you might recognize. For example, if you add 1 to all those, it would be 3, 9, 27, 81, and 243. That's one that you guys might recognize throughout that pattern. You're not going to recognize this one, but you'll definitely recognize this one. Okay? Now, as we look at this one, if you notice, what are we doing to get from here to here, here to here, here to here, so on and so on? Multiply by 3. Okay, so we have a factor of 3. This right here they call a geometric sequence. Okay, geometric means you're multiplying by the same number every time. Okay, now a geometric sequence, there was a fancy formula for us, but basically you're going to have whatever the base is. That's how many 3's that you want in there. So that's like a 3. We're multiplying by 3. So that's why it's base 3. Okay, and then we just raise it to whatever n power makes the first term work, and then we subtract whatever gets us to the other ones from there. Okay. So that they call a geometric sequence for that. We're gonna do some more when we practice that, but for right now, that's what they call a geometric sequence. Okay. All right. Feeling okay so far? I hope. Okay. Let's do what's that? Oh, I thought you asked for homework. I was like, you're crazy.
What did I say?
Not even close to what you said. Really? Okay, so go ahead and find the first 5 terms of this guy.
I don't know how.
Yeah, start with 1.
This one's going to be the same for everything. From 1 to 5. What we're going to.
5 terms. Yep, let's go from 1 to 5.
Oh, I said 10.
What? Somebody's figured something out. I like it.
Wow, it's not like hard. Everybody said it so far.
Really?
Yeah.
Really?
Everybody's been with some sequence.
It's not subsequence.
I know, but I mean it's not hard. Oh, but you're not supposed to take the sum. So what does that leave you?
Hey, I just, yeah.
Now you just gave it away, Sam. No big deal.
I'm just saying, feel free to mess around with your calculator. See what you can find.
Using tables is really easy.
Tables are fine too. Tables are fine too.
All that
Oh,
shit.
3 minus 1.
Would you like to plug yours in and show everybody?
Mm-hmm.
Okay, here you go.
Just do right there.
See, not everybody has this. Anyways, feel free to mess with stuff. Now yours might not have it's got like math print or math thing on there, so you can see that it's raised to the x power. You might just have to do a little caret to the x, you know. So every calculator is a little different. Yeah, hers is cool like that. So most of the newer ones have that little, so the print looks nice. Looks nice and pretty. So.
Watch my picture.
All right, so what is it going to do? It's 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2. Sounds pretty good. So that one's what they call an alternating sequence. Okay, it alternates back and forth from one thing to another. Okay, if I plug in a 1 right there. Now notice with this power thing right here, make sure I'm on the right stuff. This power stuff that I have right here, all this thing is doing right here, which we're going to have a bunch of those. What are you throwing fish at me? This power right here, this -1 to the end, all this is doing is basically flip-flopping the sign, right? We're basically going from 1 to -1, 1 to -1 back and forth. So that's why that pattern works with the 2, 4, 2, 4, 2. Okay? All right, last one of this, finding the sequences, and then we'll do some a little bit harder stuff. Let's go ahead and do some B sub n. I know this isn't really calculus yet, right? We're getting there. We're so close. Let's do n squared over n plus 1 factorial.
Oh my gosh.
What's a factorial?
How do you put that?
Would that be
You can put that in your calculator. Yeah, we have done stuff like this before, yep. So we're going to find the first 5 terms. B sub 1, B sub 2, B sub 3, B sub 4, B sub 5. Find the first 5 terms. Once again, feel free to cheat a little bit. Somebody just showboated the nice way to do it. How do you? It's the same. It's kind of the same as Math 9. Same as using Math 9.
Yeah, you got it.
And then with the
Comma x, comma whatever you're going from 1 to 5 on your sequence there. Okay.
How do I do factorial?
I didn't understand what you meant.
What's a factorial again? So it'd be the first one is n plus 1 times.
Yeah, let's remember how factorial works real quick. So if I did 5 factorial, for example, you take whatever the number starting is, and you multiply it by every number decreasing by 1 all the way down to 1. So you're going to go 5 multiplied by 4, 3, 2, and 1. Okay? So that's the factorial for this one. Okay, so that's how 5 factorial works. So if you were to plug in b sub 1, right, you're going to plug in a 1 there. 1 squared is 1. Divided by 1 plus 1 would be 2, so there's going to be 2 factorial. 2 factorial is just 2. 2 times 1 is just 2. So we have 1 over 2 for your first term. So your first term is 1/2. Okay? Second term, plug in a 2. 2 squared is 4. So there's going to be a 4 over, plug in a 2 would be 3 factorial, which is 4 over 6. 2 over 3. Now, on your pattern, it might be good, at least when you're recognizing patterns, is leaving it in the unreduced form. It might make the patterns more obvious. Okay? Plug in a 3. 3 squared is 9, so it's going to be 9 over 4 factorial. So 9 over 4 factorial. 24. 9 over 24. Does 9 over 24 reduce? I don't think it does, actually. Oh, yeah, it does. Yeah, 3/8.
Oh, you have to do n squared.
Yep, got to do n squared. Okay, b sub 4, fourth term in there. Plugging in a 4, 4 squared is 16. So 16 over 5 factorial, 5 factorial. Notice the numbers in the bottom are getting big really fast, okay? Factorials have a way of doing that, okay? So it's 16 over 5 factorial, which is 120. I think it's 120.
120. That's got a bunch of
Hey, that's a good observation. We're not there yet, but yes, good observation. 16 over 120, right? What does that reduce to? What is it?
Divided by 2. 8.
It's approaching 0.
60.
4, it's going to be 30. 2 15ths, right? Okay, so 2 15ths, okay? 2 15ths. And last one here, b sub 5. Okay, b sub 5. We're going to get, 25, and then divided by 6 factorial. And so 25 over 720. I think that's right. And then 25 over 720, well, that should go in there, right? At least 5 goes in there.
Yeah.
So what is it, 5 over 124? 144? Okay. Okay, so 5 over 144. Now, one thing to notice is what kind of that sequence is heading to. What you think it's going towards. It's going to 0 on that one, right? Eventually it's going to get there. Actually, eventually get really close to there, but not actually hit there, okay? Feels like calculus, but we're going to get there. Feels like limits. We're going to get there later, okay?
So are we gonna like do limits
Oh, you better believe it.
Okay.
What's up?
The same kind of stuff I'm actually going with my table right now.
Oh, that's good. That's good. I actually was talking to a buddy of mine, and he's a computer programmer. He's like, so I thought of you the other day because I looked up Taylor series he's a programmer. He was computing like margin of error for processing on a CPU he was using, and he had to use Taylor series for it. So my DC kids are gonna like that. So we haven't got there yet, but we'll be finishing. All right. Before we start recognizing sequences and how to write our a sub n term or whatnot, real quick, let's do a quick little review of factorial work because I think that's going to be a little confusing. We are tonight going to have some just reducing some factorials, like 25 factorial over 23 factorial, and your gut shot reaction would be to put that on your calculator. However, I think it'll say 25 factorial, it'll say overload or overflow, or it'll probably yell at you. Okay, it's a little too big. Okay, if for some reason. Did it actually work?
It worked. I see to the 25.
Oh, okay, you did. Okay. Try to do it without it. See if it yells at you. Okay? What's up?
I put it in and it gives me a decimal that says E is 25.
Oh.
So,
Oh, okay, so it does. So, okay, now if I did 125 over 123, 125 over 123, it would probably yell at you then. Okay. So if I did 25 over 23, both on the factorials here, first you just want to kind of reduce those and see what they're going to look like. 25 factorial, remember, is 25 times 24 times 23 times 22 times 21, all the way down to 1, right? You don't want to write them all out, but that's what it's going to be. 23 factorial is going to be 23 times 22 times 21, all the way down to 1. Okay, those are going to go dot, 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 all the way to 1, dot, 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 all the way to 1. Okay? Cancel all the way through. These guys cancel, those guys cancel. You're left with 25 times 24, which was 6, what did you say? Right on 600. Okay? So that simplifies, reduces to 600. Okay? What's up?
it didn't yell at me, it gave me 600.
Oh, 125? Nice. Wow, we got to go bigger then, right? So how about 1125 over 1123? See what it is.
11,
There's got to be a breaking point for it, right? Eventually. So, all right, let's do one more that's a little tougher. Let's go n plus 2 factorial.
Overflow.
Overflow. Cool. Okay, n plus 2 factorial
It's
over n factorial. Let's go ahead and reduce that a little bit. Now we want to try to expand this, try to write this in what they had that factorial version, that factorial form. So on the bottom one's pretty easy, at least I think. You start at n, so it's going to be n, multiplied by 1 less than n. Okay, so it's going to be n minus 1. Multiplied by 1 less than that guy, n minus 2, right? n minus 3, n minus 4, blah, 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 all the way down until we get down to multiply by 1. Okay, and we don't know how many terms are in there. We don't really care how many terms are in there. We just want to kind of write that expansion version. Now, n plus 2 factorial is going to be n plus 2, multiplied by 1 less than that, so n plus 1. 1 less than that, so n. 1 less than that, n minus 1. Dot, 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 all the way down to 1.
So just n plus 2 times n minus 1.
So it's just n plus 2, n plus 1. That's the simplified version of that guy right there. Okay?
Okay.
Does that idea, logic make sense? We're feeling pretty good about that? Okay, let's go ahead and write some of our own sequences here, some of our own nth terms, and then be good. What's up? Because you're not paying attention and laughing.
That's okay, I got it. Got you.
It's not your fault. Don't blame yourself. I blame society. I blame society.
Yeah, I'm sure if it has like.
You said this was a cute shirt.
Irritating.
I mean, it's a good shirt.
I think you said a cute. I think you said a cute shirt.
I think my shirt's pretty cute.
I think that is.
It is cute. Hey, we almost matched. Nice. Yeah. All right, even them. I see how it is. Sure. Didn't even say please.
Would Barbaro have said please?
No, he'd come in at midnight. Is that better? Okay. Now, what we want to try to do is write our a sub n form method. We want to write what they call the apparent nth term. That's kind of how they say it, okay? We're looking for our a sub n formula, though. Basically, if I'm going to find the 12th term, what formula would I use to plug in a 12 to figure out what it would be. Now on this one, sometimes it's kind of hard to see how it's going to work, but when you do these sequences, you want to look at basically the numerator and denominator separately if you can. So I would just do one each individually. So basically you're looking at the top sequence of being 2, 4, 8, 16, 32. That's your pattern that you're looking for, okay? So you want to try to identify what pattern is going on here. What are you doing differently from the 2 to the 4 to the 8 to 16, right? What's that going to be?
2n.
A 2, right? It's going to be power of 2. Now, that's going to be a geometric ratio, which means we're going to multiply 2 raised to some power, okay? So we want to do 2 raised to some kind of power of n. So we have to do a little bit of guessing and checking here. Well, let's say I did 2 to the n. It could be 2 to the n plus 1. It could be 2 to the n and then minus 1 right here. We're not really sure, okay? So what we do is we just kind of check some answers, right? So plug in a 1. 2 to the first is 2. Hey, 2 to the second is 4. 2 to the third is 8, okay? So our numerator is just 2 to the n. That's not too bad. At least I hope pretty easy, okay? That's a geometric sequence. The denominator goes 1, 3, 5, 7, 9, right? So what's your common thing there? 2n minus 1. You get to jump right to it. Okay, fine. 2n minus 1. Okay, this one's arithmetic on the denominator. Okay, arithmetic sequence. And so if I plug in a 1 right there, the difference is 2, so that's why it's a 2n. And then the minus 1 gets me up for my first term, basically. Okay, so that's why that one works. Now, if I wanted to find the 10th term, I can just find a sub 10 now, and just plug in a 10. See what I get. So I get 2 to the 10th, then divided by 2 times 10, minus 1. 2 to the 10th is a pretty big number, not sure what that is. And then 20 minus 1, so 19, so whatever 2 to the 10th gets you. Okay? What is it? 1024. Okay? That number sounds familiar, 1024. I've seen that before. You know where that number comes from?
It's a date on a calendar.
It is a date on a calendar. What about in the computer world?
That is
It's the dimensions of the screen on one of them. Yeah.
hey, it's the
If you were
DECA
to-
test.
It's the what?
The number for the DECA test. Like the practice test is 1021. No, actually, this is 1024.
number.
It's that number. If you, yeah, really. It's actually if you go by a gigabyte anything, a gigabyte is 1024. It's 1024 megabytes for 1 gigabyte. It's not exactly 1,000. Anyways, so
That's why it's 512.
that's why it's 512. Yeah, that's why it's 512. It's half 1024. Interesting.
How many bits is that?
I remember when I bought my first MP3 player, it was 256 megabytes, and that was huge.
It's expensive. It was
It's a
crazy.
megabyte or
Quarter of
gigabyte?
V6, quarter of a gig.
Gigabyte is bigger.
How many megabytes are in a gigabyte?
Your mom.
1024.
Yeah, that's what you were saying.
Okay, so
Just pull out your mom's
you said it
right
confusingly.
Hey.
Oh, you get negative, positive.
I ran out of room on my dots. Okay, so let's figure this sequence out, and then we'll cut you loose.
I'm just kidding, I'm not making sense.
Still pre-calculus a little bit, actually.
I'm still in trade.
We could have done the pre-calc, or the could have done the calc part, but I think people are going to struggle on this. I could be wrong.
Oh, you're right.
I probably am.
I multiply by negative 4 every time. Next to n plus 1.
Okay, so the denominator might be easier to recognize here, maybe. No?
It is.
We have 1, 2, 6, 24, 120. Here I multiply by 2. Here I multiply by 3, multiply by 4, multiply by 5. So I'm multiplying by one successive bigger number, right? That sounds like a factorial. So plus, they're getting really big really fast. Okay, so that's also kind of a nice way to check out, hey, it's a factorial. So on this one, I would just say it's a factorial. So this is going to be n factorial. And I don't know if I need to go n plus 1 factorial or 2n factorial or
Wait, but how does it get bigger?
n plus 1 factorial. Because if I want to find a sub 5, I plug in the 5 right there. So it would be 5 times 4 times 3 times 2 times 1. If I plug in a 6, it would be 6 times 5 times 4 times 3 times 2 times 1.
Okay.
So it's going to get bigger by a factor of whatever the next n term is going to be. Okay? So denominator I think is going to be just n factorial. If I plug in a 1, it gets me a 1. 2, 2, 3, 6, 4, 24. So I'm feeling pretty good about the denominator. Okay? N factorial. Okay? Now the numerator, I'm going 1, 8, 26, 80, 242. Numbers that we might not recognize right away, but they're really close to numbers that we recognize, right? What if we add 1 to each of those? A little foreshadowing, we already did this one. Okay, if I add 1 to each of those, right, this would give me 3, 9, 27, 81, okay? So I need to go one more of whatever number it is, okay? So this one I need to take one number off. So I'm going to go minus 1 of a power of 3. Now my power of 3, that's my base. That's what I would multiply by to get from 1 to the next if I add 1 to each of them. Okay? Now this one, if I were to add the 1, it would be a 3, it would be a 9, 27, 81. You can see you're multiplying by 3 every time you get to those. Okay?
Wouldn't it be like
Now,
-3?
now we'll get to the negatives in a second. So this would be 3 to the n power. Okay? That would give me those numbers if they were all positive. Okay? Now the negatives right there, the negatives, we just have to make that quick little fix. The negative, you really want to just think of this as like a -1 sitting in the front, multiplied by whatever the fraction is. This one you want to think of as a -1 sitting in the front, multiplied by that fraction. Okay? So to get the negative to alternate like that, all we have to do is multiply this guy by a little alternating trick. And that trick is take a -1 and raising it to some kind of power. Okay? And that'll switch the sign back and forth. Okay? So if I go -1 to the first power, that'll give me an odd number, or I'm sorry, a negative number. Okay? So a negative number, I want the first to be negative, so I want that to be an n or just a regular n. Okay? If let's say that the first one was positive and the second one was negative, you might do like an n plus 1. Okay? And that'll switch where the alternating place goes. Okay? You could also do n minus 1. Okay? N minus 1 would also work. Usually plus 1's a little safer, so it stays positive, but anyways. That's one way to make that sign alternate. Okay? So if you have an alternating sign, don't freak out. Just do the -1 to some kind of power. That fixes that part for you. Okay? So that would be my equation. That would give me any number in that sequence. What's up? You look like you're halfway on a question. You figure it out?
Can you do like a piecewise sequence? Is that possible?
Hold on. Let me think about that for a second. I like that question, but I didn't think about it.
What is U? Okay.
Every other.
Every other row.
Every other.
Ooh, I don't know if the 25 to 35 is going to work. Hold on. 25, 7, 9, 3. It's not.
Can it be equal?
Okay, so go down. 3.
Yes.